This is a special type of LPP in which the objective function, which is the objective function, is to be find out using an optimum number of allocations to a equal number of facilities or persons, right? Here we make the assumption that each person can perform each job but with varying degree of efficiency. Obviously a person can probably do every kind of job but with varying degree of efficiency. For example, a departmental head may have four persons available for assignment and four jobs to fill. Then this interest is to find the best assignment which will be done in the interest of the department. So what is the general formulation of an assignment problem? It is denoted by a matrix n into n, and the matrix is called CIJ, called a cost, which is also called a cost effective matrix, where CIJ is the cost of assigning ith person to jth job. That means one person, one job, and the CIJ is the cost associated with that particular person for performing that particular job. Effectiveness matrix, this is a kind of matrix which we are looking for. So here there are n number of jobs starting from 1 2 3 j and n, and there are n number of persons 1 2 3 I and n, right? So the cost effective matrix is like this. So the C11 is the cost of the first person performing job number 1, and C12 is the cost of the first person performing the second job. Similarly, C13, sorry, right? It's the cost of the first person performing the third job. So this is how a cost-effective matrix or an assignment problem looks like. This is the mathematical formulation of a assignment problem. This is just a general formulation, right? A person can be assigned to n jobs in n factorial possible ways. N factorial means that a person can be assigned a particular job in n number of ways. There is no limit to that, right? One method may be to find all possible n factorial assignments and evaluate total cost in all cases. Then the assignment with minimum cost will give the optimal assignment. But this method is extremely laborious. For example, if n is equal to 8, then the number of such possible assignments is 8 factorial. That means 8 factorial means 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1, which comes out to be 40320 ways, right? So evaluation cost of all these allocation will take huge time. Therefore, there is a need to develop an easy computational technique for the solution of assignment problem. Right. So this is the mathematical formulation of an assignment problem, which I'll be discussing in this lecture, and then we'll be going through the first method, which is called Hungarian method. We'll be solving one question as well, right? Using that method, it's called reduced matrix method as well. First of all, we'll look at the mathematical formulation. So here, this inverted M, I would say, denotes that it is a summation, right? I is equal to 1 and j is equal to 1 raised to the 2n Cij xij into xij, where xij is 1 if the ith person is assigned to the jth job. That means if a person is assigned the jth job, I mean ith person is assigned the jth job, then he'll get a 1 rupee, and if not assigned he'll get a 0. Obviously if that person is not doing anything, how will give you the money, how the person will be getting the money, right? So similarly, subject, there are some conditions to that, right? So xij is 1 when j is equal to 1 till n. It can take any values till n, 1 2 3 4 5 6 7 8 9 10, any values, which means that only one job is done by ith person. That means one job, one person, not more than that. That means again means that one person can only do a one kind of job. Other than that, will that next job will be, I mean no other job will be assigned to that person if one job is assigned to that ith person, right? That again means that one person can be assigned one job. So I was talking about the reduction theorem or Hungarian method. If in an assignment problem a constant is added or subtracted to every element of a row of the cost matrix, which is Cij, which I've already discussed in the previous slides, then an assignment which minimizes the total cost for one matrix also minimizes the total cost for the other matrix. So in assignment problem we are primarily dealing with the minimization problem because we want to, I mean, minimize the cost of the production unit or the company, right? So that's why we are looking at minimizing the problem, minimizing the total cost of the production and total cost of doing a particular job, right? So how we do that? We use that Hungarian or reduced matrix method. So this is the matrix where four jobs are there and four men are there, right? One, two, three, four, and one, two, three, four jobs, right? So cost of doing first job by the men one is always 12, right? And cost of doing the first job by the second man is 30, right? And cost of doing job number one by third man is 21, and cost of doing first job uh, by the fourth man is 50. So you will be thinking that why don't we assign that first person the first job, because it's taking the lesser amount than the other three. But we are not looking here for one job only, so we are looking for a overall reduction in the cost. That's why we'll be allocating the jobs using this Hungarian method or reduced matrix method. So how do we do that? This is the first step. So the first step says that select the minimum of each row and subtract from all the elements of corresponding row. That means that you have to take the first row and subtract from it. For example, in our case, first row has 12, 30, 21, and 15. So minimum will be 12. So I'll be subtracting 12 throughout from the first row. That means 12 minus 12 is 0, 30 minus 12 is 18 again, and so on, right? So this will be the my first row. Similarly for the second row, and similarly for the third and the fourth row, right? So this the matrix will look like this after subtracting uh, minimum from each rows, and I'll be getting this kind of results, right? The step 2 is select the minimum of each element and subtract from all the elements of corresponding column. Again, the similar exercise has to be done using the column now, right? So in every column I have to select, suppose in column number 1, my smallest number will be 0 again. So I'll be subtracting 0 from 0, 9 from 0, 23 minus 0, and 9 minus 0, which will all obviously give me the same column, first column. Similarly for second row, similarly for third row, and I'll be getting this kind of matrix, which is this one. So 0, 9, 23, 9, 14, 20, 0, 12, 9, 0, 3, 14, 3, 22, 0, 0, right? So I'll be getting this kind of matrix. So I'll be just using that for the now for the allocations, right? Now our job is step 3, which is a very important step, I would say. Starting with row 1 of the matrix obtained in step 2, the matrix which we have obtained in step 2 will be starting from that in the third step. Examine rows successively until a row with exactly one zero element is found. Mark square at this zero and an assignment is made there, right? For example, in our case, if I say that in the first row, uh, the 0 is there in the first C11, I would say, right? So I'll assign the square matrix, I would assign square to this 0 number 1, right? And the next step is, as an assignment is made there, okay, then mark cross at all other zeros in the column in which we marked square. If there are any other zeros in column number 1 or row number 1, I would be marking that particular zero as cross to show that they cannot be used to make other assignments. Proceed in this way until the last row is examined, and we have to do this until the last row and all the assignments probably I would say are done. So what I have to do is I'll be doing first of all, so I have assigned square to zero number 1, which is C11, and this particular job is assigned to men number 1, right? So if there are any other zeros in this particular column, column number 1, I'll be marking it at, I'll be crossing that particular call, I would say that a particular zero, right? Suppose again I'll go in column number 2, so I'll be assigning square. Oh, sorry, I'll not go in the column number 2, I'll go in directly in row number 2. So I'll be assigning 0 in the row number 2, which is my probably C323. Okay, C23, right? So if any other zeros are corresponding into this row, I'll be crossing them outrightly, right? The next will be as I'll be assigning 0 to this particular, I would say third, in the third row, and I'll be crossing the last 0. So for that I have written again, after examining all the rows completely, please similar proceed similarly examining the columns. Examine column starting with column 1 until a column containing exactly one unmarked zero is found. Mark square at this zero, mark cross at all the zeros in the rows in which we have marked square, right? Proceed in this way until the last column is examined. Suppose in row number 3 there are coming two zeros, right? So how do I assign square in that? In that case I have to look back to the cost matrix, and I have to look which zero has the lowest number. So I'll be assigning the job to that particular who has a cost effectiveness. Suppose in this case, my case, men 2 has a lowest, has probably is taking I mean less money than the fourth man. So I'll be assigning this square to the in the third column to men number 2, and I'll be crossing the corresponding zeros in this particular row. Next is I'll be assigning, so the last one will be I'll be assigning this particular column to this one. So I'll be getting this answer like this. The row number 1, in row number 1, first job goes to the first man. In row number 2, the second job goes to the third man. In row number 4, the third job goes to the second man, and in row number 4, fourth job goes to the fourth man. So I'll be calculating the cost effectiveness here. I'll be calculating the total cost here, right? Continue these operations until successively we reach to any situations. All the zeros are marked using the square or cross. The remaining unmarked zeros lies at least two in a row or column. In case we have the maximal assignment as much as we can, and in case still we have some zeros to be treated, for which we use a trial and error method to avoid the use of highly complicated algorithm. Now there are two possibilities. If it has an assignment in each row and each column, that is the total number of marked zeros is exactly equal to n, then the complete optimal solution is obtained. That means if all the jobs and all the men are occupied, so I'll be getting the optimal solution for that. So the answer will be first. Okay, so till now we have discussed the assignment problem using the reduction matrix method or Hungarian method, which was a minimization problem. So we are discussing now the unbalanced transportation problem. So unbalanced transportation problem or an assignment problem, I would say. An assignment problem is called an unbalanced assignment problem whenever the number of tasks, that means the jobs, are not equal to the number of facilities or persons. That means that the jobs are more, or probably the persons are more than the jobs, right? So that situation is called an unbalanced assignment problem. Thus, the cost of matrix of an assignment problem is not the square matrix. So to solve assignment problem, we need to have a square matrix. For that purpose, we need to balance it out. First of all, if it's an unbalanced assignment problem, then we have to solve using the Hungarian or reduction method. For the solution of such problems, we are the dummy rows add the dummy rows and dummy columns to the given matrix to make it a square matrix. Suppose if the number of jobs, or so wherever the scarcity is there, so we'll add dummy variables, dummy rows or columns to that matrix to make it a square matrix. The cost in these dummy rows or columns are taken to be zero. That means that in entire row or column, the dummy, it will be zero. Now the problem will reduce to the balance assignment problem and can be solved using the assignment algorithm, which we have discussed earlier, which is called a Hungarian method or a reduction matrix method, right? The last one, which is a maximization problem, since we have discussed about unbalanced assignment problem and the minimization cost problem. So there is also a maximization problem where the objective function is to maximize the profit, right? Sometimes the assignment problem deals with the maximization of the objective function. The problem may be assigned to persons to the job in such a way that the expected profit is maximized. Such maximization may be solved by converted into minimization problem. This is done converting the profit matrix to cost matrix in either of the following ways. That means that if the profit matrix is given, we have to convert that matrix into cost matrix, and using these two ways, probably one of them, right? And then we can have solve it using the Hungarian or the matrix reduction method. Subtract each element of the given matrix from the greatest element of the matrix to get the equivalent cost, that is loss matrix, right? That means that the greatest number, the largest number is has to be subtracted from the each element of the matrix, and we'll get a cost matrix. Or place minus sign before each element of the profit matrix to get the equivalent cost matrix. So, or you can place a minus sign using your software or your pen and paper onto the profit matrix, and it will be converted to a cost matrix, and then it becomes a minimization problem, and then we can solve using the assignment algorithm, right? So that's it for the assignment problem. We'll